Here we go again, and we're going to continue the story by looking at lines and equations and combinations of vectors and some examples. Then we are going to get into something called matrix algebra. We'll take a look at what is known as coefficient matrices and total matrices and how they relate to lines and systems of equations. Let's dive into it. The first topic for today is lines and equations. We'll ease into it, which is nice for midweek. Let's start with this example. What is a similar alignment? And I'll show it with an example. You're ready to start university and tackle equations of this difficulty level. This is an example of a form right next to her. And there's just one unknown. It's called x. And we need to find a real number x, which when multiplied by 2 gives 6. We call that a linear equation because the only thing that has happened to x is that x is multiplied by a constant. So x is not squared. If it were, then it would not be a linear equation. It also does not say 2x sine of x. If we write it with 6, it still would not be a linear equation. If the only thing that happens to the unknowns in an equation is that they are multiplied by constants and then everything is added together, we call the equation linear. So this is an example of a linear equation. We can solve it by dividing by 2 on both sides. So we get 6 divided by 2 as the solution, also known as a tree. And even though this equation seems incredibly simple, you can actually learn by looking at equations that this type contains all the essentials about lines and slopes. So let's try another example, and we'll gradually uncover some of the theory. So here comes example 2. What if it says 0 times x equals 6? Up here it says 2x equals 6, and the solution was x equals 3. Now we are trying to look at another line, which is that 0x has to equal 6. And if you think about it, that line will have no solution, because no matter what number I insert in place of x, when I multiply by 0, it gives 0. So the hope that it would result in 6 completely vanishes. That hope evaporates into thin air. There is no solution. So what we saw earlier is that a straight line can have exactly one solution, but there's also the possibility that it has none at all. So up here we have exactly one solution. And the word precisely in mathematics means exactly one, meaning one and only one, precisely one. And down here, this is how people usually write it. If you read it out loud in Danish, it says that the solution space is empty, so there are no solutions. So there are 0 solutions here. I did not write that 0 is a solution. I just wrote that there is no solution. Some of the solutions I like because 0 times 0 is not 6. Here comes another example. What if I have an equation that says 0x equals 0? So now I'm looking for a number that, when multiplied by 0, gives 0. That was a nice and easy task, because all numbers work. No matter what number I put in the placeholder, when I multiply by 0, I get 0. Even 0 works. 0 times 0 is 0. 1 works. 0 times 1 is 0. And so on. So here we have an example of a linear equation with infinitely many solutions. So here we are. Infinitely many solutions. So you could say that as long as x bar is some number, it will solve the equation. And now we have basically learned everything there is to learn about lines and equations in principle. Or at least we have learned the most important things about lines and equations. If you have a linear equation, there are always 3 possibilities, and there are no others besides these 3, making up the entire possibility space. Either there is exactly one solution, none at all, or infinitely many. There are no other cases. And this is true whether you have 20 equations with 20 unknowns, or 2 equations with 2 unknowns, or 1 equation with 1 unknown.
This applies to all linear lining systems.
And for all linear equations, it's like this. Either there is exactly one solution, no solution, or infinitely many. So that was the first and most important thing we've understood about linear equations in this context. So you can have a system of equations. Here comes example 4. And when you eventually try to work with systems of equations yourself, you can cleverly start with the solution and then see if you can find it yourself. So if you start with the solution, you know what the answer is. So let me now invent two numbers. x1. It's 2 and x2 is -3.
So I just started making up the solutions.
Now I'm giving myself the task and trying to solve it to see if I can figure that out, to see if I can get some calculations. So let's say we start knowing this and start knowing that. You typically won't know these if you get an assignment from your teacher. That's exactly what you need to find. But if you give it to yourself for practice, you can begin by writing down the solutions, so you know if you've calculated correctly in the end. And then I'll just make up some equations. Here's equation 1. If you take 2 power 1 minus x2, what do you get? It's just something I'm coming up with. So I make up a number here and a number here, -1. And then I multiply it by x1 minus x2 and just calculate what it results in. 2 times that number, that's 4, minus -3, which is +3 added to 4, that makes 7. So I think that if x1 is 2, and if x2 is -3, then this is true. 2 times 2 is 4, minus -3, which means 3 added to 4, that is 7. So that is an equation. Is this a linear equation? Yes, it is, because the only thing that happened to the unknowns x1 and x2 is that they were multiplied by constants and added together. Look, x1 is multiplied by 2. X squared is multiplied by -1, and then everything is added together. That way, it has a line on its own. Let's try to do another calculation. Let's try saying -3 times x1 plus x2 and figure out what it gives. So -3 times 2 is -6. -6 minus 3 is -9. So this should give -9. And now I've given myself a task. I could pretend I don't know this up here and try to see if I can figure it out. And in this way, you can practice solving lines and equations yourself. And you can always practice it completely independently from others. You start by coming up with solutions, then you write down some equations that you've thought of. Then you try to solve the equations and see if you get them right. And the method I showed you last time to solve it, we can try using it again. And the method I showed you last time is to look here, 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 and here. All the numbers that are multiplied by the unknowns, you write them down in a rectangular table of numbers. And such a rectangular table of numbers is called a matrix. And such a matrix is called a coefficient matrix. And you write it as a capital letter with 2 lines underneath. The 2 lines underneath indicate to the reader that it is a matrix being discussed. You're used to seeing an overbar or an upward arrow, and then it is a vector. But now it is a matrix because a matrix is a rectangular table of numbers. And if it is to be a coefficient matrix, it must include all the coefficients of the system of equations that are put into this matrix. So you simply read 2 minus 1, because hidden there is -1 multiplied by x2 minus 3 and plus 1. And this is the numerical scheme here. 2 minus 1 minus 3 and 1.
And that's what I have.
In the matrix. And you name a matrix based on how many rows and how many columns it has. And you can see here there are 2 rows and there are also 2 columns. Therefore, it's called a 2 by 2 matrix.
So this is
A 2 by 2 matrix. And that is a very specific matrix. It's called a coefficient matrix for systems of equations.
Kovifichet.
Matrix. From the system of equations written up here.
Oh, I have been sitting for so
It
long.
says 7 and 9. And with those 2 numbers in a column vector, you get what's called the right-hand side. And we usually call it B. If there are more than 3 dimensions, you put the line underneath. But we are in 2 dimensions, as there are only 2 numbers. So in our situation, you would put a vector line above. But if there were 5 equations with 5 unknowns, when you wrote down the entire right side with the 5 numbers, you'd call it B and put a line underneath instead. But that's something we only start doing when the dimension count is higher than 3, because then it is not a geometric vector. It is more of an abstract vector. So my right side would then come to 7 and 9. Sorry, 7 and minus 9. Just like that. That's what we call a column vector. You also have a row vector, where you just write the numbers next to each other. But this here is a column vector.
And here it represents the right side.
Is there one in the system? And finally, you have one more column vector that contains the unknowns. And how many unknowns are there? Well, there is x1 and there is x2. So there are 2 unknowns. And therefore, the unknown column vector will contain x1 and x2. So it looks like this. X vector contains the 2 unknown numbers x1 or x2. So it is also a column vector. And it is a beam scale that contains the unknowns. There's one in the hair. Unknown variables, x1 and x2. If you take that coefficient matrix and combine it with the right-hand side, you get what is called a matrix.
A total.
And you'll see that on the next board.
And this here was panel 1. So we'll just continue with example 4 over here.
And I hope it's okay that we have to go out here.
So example 4, put here.
And now we introduce the concept of the total matrix, And you write a big T to abbreviate the word total. And then you simply merge the coefficient matrix A with the right side B. So what it says here is to imagine merging the coefficient matrix A with the right side B. The resulting matrix is called the total matrix of the system of equations. So it will rise 2 minus 1, minus 3 and 1, and then you draw a dotted line, and then you rate the right side, so you merge it with the total matrix. Here it should say 7, and here it should say minus 9. And as you saw last time, all it takes is to write up the augmented matrix and work with it to solve the system of equations. Because here is all the information about this particular system of equations. Notice that you cannot see x1 or x2 written anywhere. But when you see this, your brain should think that 2 over 1 minus 1 on 2 equals 7. Minus 3x1 plus 1x2 should equal minus 9. That's what you should think when you see it. And now we'll see if we can get this into reduced row echelon form. It's something I just mentioned last time that exists. And you do that by performing row operations. So what are row operations? That's something I haven't really gone into much detail about. So I will explain it now before I do it. Row operations mean what is allowed to do in a matrix. Here we go. All right. With any number, as long as the number is not 0. Can you also multiply by 0? But then the equation disappears. So you lose information. It's not that you cannot do it, it's just incredibly stupid. See, if I multiply this equation by 0, it says 0 and 0. Is that equal to 0? Yes. I already knew that 0 plus 0 equals 0. I am not solving the system of equations by doing this.
So you have to multiply
Go through
row
it
with a number as long as the
It
number
does not
is
make
not.
sense to multiply by 0. You get nothing out of it.
Number 2, you're allowed to add rows together. Notice that you're also allowed to multiply by a negative number. So I do not need to mention here that you can also subtract rows from one another. It is obvious. If you can add them together, it is equivalent to subtracting them from each other if you had just multiplied by a negative number first. So you can multiply a row by a number, as long as that number is not 0, and you can subtract rows from each other if you first multiply by a negative number. Add the rows together. And if you can multiply a row by a number, then you can also wait to add them together, just after multiplying by a number, of course. So you can add rows together.
And finally, one can switch 2 rows.
You can do that too. And if you think about it, it's pretty obvious why you can do exactly the things listed here. Let's start from the bottom. Why is it okay to swap 2 rows? Well, it's obvious that this system of equations will have the same solution, regardless of whether I write one equation first and the other one second, or vice versa. So naturally, if I swap the 2, it has the same solution as before. Therefore, it's allowed. You can add rows together. It is pretty obvious if you think about it, because if 2i1 minus x2 equals 7, and minus 3i1 plus x2 equals minus 9, then it must be true that the number of x's plus the number of x's and the number of x2's plus the number of x2's should give 7 plus minus 9. So you can also add rows together. And finally, you can multiply a row by a number, right? Yes, because if 2 times x1 minus x2 equals 7, if you multiply the entire row by 2, you get double the number of x's and double the number of x2's. So you should also get double the result. So because it is a linear equation, it makes sense that you are allowed to do that. Can you see it? And now let's see if we can use these allowed operations to bring that augmented matrix down to reduced row echelon form. And what was it that meant again?
Yes, that's what this means.
This means you're trying to do something with that overall matrix up there so that it ends up looking like this.
1001.
And here will be x1 and x2. So if I can work some magic with that matrix, you'll see a 1 here and a 1 here and a 0 here and a 0 there. And what will appear here will be the 2 solutions, 2 and minus 3. And it's really clever that it works like that.
And that's it.
Why does this automatically give exits? Well, it's because what you should think it says is 101 plus 0x2. And of course, that's exit. And here it should say 0x1 plus 1, 2. But naturally, that gives exit. So if I can perform magic from that form to this form, then I have solved the system of equations. And the magic only involves swaps, but you must only use swaps among these 3 rules. No homemade rain rules. You can only do this here, but it won't always be enough. Let's try to finish solving it on board number 2. So this is still example 1, which now continues over here, and I'll just delete this part. I do not have everything I need. I will leave the result here so I can remember what I came up with. So I had a total matrix that looked like this. 2 minus 1, yeah, fun. Minus 3, 1, and minus 9. And now I want to do something with it. And I will only do some of what is allowed to be done with it until I end up with something that looks like this. The first thing I think of there, I would really like for there to be a number there. That's what's happening here. And it's called a leading one. So you want leading ones all the way down the diagonal. And the diagonal is all the numbers running this way down, depending on how big the matrix is. So to get a leading one there, I can just take the top row and multiply it by 1/2. Can I do that? Yes, because I'm allowed to multiply a row by a number, according to the book on legal operations. So I do that. I multiply that by a half and get a new overall matrix, which is not equal to
Just
the old
right
one.
if you want it to be completely
So
mathematical.
we use a tilde here, which is read as equivalent to, and it indicates that this represents the system of equations. It has the same solution set as the system of equations that will now be represented here. So let's try. We multiply by half there, then it becomes 1. Multiply by half there, then it's minus 1/2. Multiply by 1/2 there, and you get 7/2. And down here, I haven't done anything. So I just copy paste -3, 1, -9. You might end up having to deal with fractions, but that is something you just have to accept. Especially if you are the one creating the problems on the board, you always risk ending up with fractions. Now that I've got a number there, I'd like to get a 0 there. You can see there needs to be a 0 outside the diagonal where the system of equations has been solved. So I'm thinking, how could I get a 0 there? Oh yeah, I could just multiply the top row by 3 and then add it to the bottom row. So I'll take the top row and multiply it by 3. We write it like this. When I have done that, I will add it to row 2. Because if I do that, it will be 3 times 1, which is 3, and 3 added to -3 results in 0. So I get a 0 there. Can you see that? So what you should read here is that I replace the old row 2 with 3 times row 1 plus the old row 2. So whatever I need to write down next will be what I get by doing what's written there. That's how you should read it. Let's try it then. So now I get yet another new total matrix. I haven't done anything to the top row, so I can quickly copy and paste it from before. And then I'm thinking, okay, 3 times 1 is 3. 3 plus -3 is 0. So there should be a 0 here. Because I'm doing the operation I wrote down that I would do here. So I say 3 times that, which is -3/2. And -3/2 plus 1, well, that must be -1/2. And finally, I should say 3 times that one, which gives 21/2, which I need to add to -9. I better think about it. 21/2 need to be added to 9, or -9, which is -18/2. I can think of it that way. And from 18 to 21, there are 3, so that must give 3/2. So I should have 3/2. Did you follow that? I multiplied 3 by row 1, or 3 times 7/2, then multiply the numerator. 3 times 7 is 21, so 21/2 added to -18/2.
But we have to add plus 3/2.
Sometimes you might need to have a little piece of paper to calculate these things, so you do not mess them up. So now I can see I got a 1 there, and I have a 0 there, and now I want to get a 1 there. How do I get a 1 there? Well, I multiply the entire bottom row by -2, because minus times minus gives plus, and 2 times a half gives a whole. So I take row 2 and multiply it by -2. And whatever I get, I'll write that instead of the old rule. And keep going with that. Up here, I've not done anything, so there is still 1 and -1/2. And the right side of 7.5. Well, 0 times -2 is still 0. It would be annoying if it wasn't, because I would have messed up the 0 that I wanted there. And I was working with that 0 in that position. Then I say that -1/2 times -2 gives exactly 1. And I like that because now I have a number in the diagonal. Then I multiply 3/2 by -2, so the 2's cancel out, which just gives -3. Well, what can I do then? Well, I could take row 1 and add half of row 2. Why is it clever? Well, if I take row 1 and add half of row 2, half of 0 is still 0. And 0 plus 1 is still 1, so I'm not messing up the 1. If I take half of 1, I get 1/2. Add that to -1/2,
And that's
and
good.
you get 0. So you'll end up with a 0 there. So now I go up here and take half of row 2 and add it to row 1. You need to do this a few times before you realize where these ideas come from. It can look a bit magical when you watch others do it. But you always have to remember that I'm looking for this structure. In English, it is called reduced row echelon form, because there are leading ones all the way down in a kind of stepped shape. So let's try doing that. And I think we're there. So I need to say that half of 0 is 0 and added to 1, it's still 1. Then I should say that half of 1 is 0 and adding it to minus 1 is 0. Then I need to say that half of minus 3 is minus 3 halves, which I should add to 7 halves to now get 4 halves, also known as 2. So now it says 2 here. And in the bottom row, I've not done anything. Notice that that is where you perform the operation. That's where you write the operation. So because it is up here, it is the top row where something is done. I have not done the other row. So here it should say 0, 1, and negative 3. When that's the case, the brain, of course, thinks,
Da.
Here's the solution.
but what it says now, 1 times 1 plus 0 times 2 equals 2. So what is x1? 2. Knowing this, we have actually figured out the problem ourselves. And you can do it as many times as you want at home. And I recommend doing it just as many times as it takes for you to start feeling like you really get it. Not less than that, but preferably more. Do it more often, but not less. Because if you have not spent time with it yourself, you will just be going in circles until the monthly exam. I'm always scared to death before I have to do it because it is super easy to make a mistake. Fortunately, it went well this time. Here it says 0 times 1 plus 1 times 2 should equal negative 3. So x2 must be 0. Minus 3. Happy thoughts.
That method is super smart. So we just need to practice it a bit.
In class. If you want to pause and count, now is the moment.
Okay. Here we go again, and now I'll show you an extreme.
For example, instead of 2 equations with 2 variables, you have 3 equations with 3 variables. And that's when it really starts to be smart to know the method you just practiced. So here comes an example. And just interrupt me along the way if what I'm doing doesn't make sense, because it's important that you get this, as we will be assigning homework too. So there are some tasks you need to solve based on this. Jonas? Yes, I have actually prepared some, but I'd like to go through an example afterward, if you need it, which I've worked out on the board. So here's a story about 3 people. One of them is named Anders.
And the next one is called Berm.
The last one is called Chantel, because then it is actually the letters A, B, C.
And imagine that Anders, he has
55 krona. That's how much money he has. And imagine that Berge has 35 kroner. And imagine Chantel has 30 krona. It's a problem from a math competition in the Gilmore contest for high school students. And if they had taken this course, everyone would have solved it. But they didn't have it because they were high school students. So only a few people in all of Denmark could solve the problem. But now you'll see how tasks can be solved with the help of the theory about
That's
line.
an equation.
The first thing you can start by looking into is how much money Anders and Berge have made together.
It's just a little bonus for them, right?
That plus that makes 75. And then the 5 makes it 80. And then, wait a bit. Where did I write the correct numbers? No, 65. Sorry. So you add those two together to get 65. And then add the 5. And you have 70. At 70 plus the final 50, that's 120.
So A and B and C, that means the amount for Anders, and that means the amount
These
for
are
me.
amounts that are a bit daunting. And they are the same as 120 kroner. Do you all agree? Now listen, if Anders gives as much to the children's home as he has himself, oh, how much do you have?
We're hitting the road.
35. So Anders should give as much to Berge as Berge already has. How much should he give him? 35. Are you in on that? Afterwards, Berge has to give himself as much as he has. So when Berge reaches 70 krona, he has to give away 30. Are you following that? How much will he have left at the
It
end?
is used. Here I am.
Yeah.
When Chantal has received 30
She already
kroner,
had some. So she was up to 60. Now she needs to give as much to Anders as Anders currently has. And how much was that Anders had now? All right, he started with 55, gave away 35. So he is down to 20. So he needs to get those 20 back. So he also ends up with 60.
And Chantel had gone up and had 60, but gives
20 down, so she ends up at 42.
Okay. So now I can ask you a riddle. 3 people from BRC have together 120 kroner. We don't know how much money the main topics have. Yes, they know that, because I revealed it beforehand. But we assume we do not know. First,
We
AL
collaborate as Beehive online, no?
Then I give B as much to C as before.
C already had some. Finally, C gives A as much as A currently has. And after these exchanges, they each had 40 kroner. And then they asked in the math competition, how much did Anders, Berger, and Chantal have to start with? The answer is 55, 35, and 30. We know that because we started with the answer. But now I will show you how to find the answers. 55, 35, and 30 using the theory of linear equations. Are you ready? So let's say we need to set up the equations. What do we know? If the symbol A and the symbol B and the symbol C represent how much money they originally had, what can I say then? Because they have 40 kroner in the end. First, we take what A has, then we subtract what they're supposed to give to B. Isn't that right? So that person first gave something to B. But what happens in the end? In the very end, A gets as much on top of it as they currently have. So this needs to be multiplied. And now I must conclude. Oh, okay, now we need to think. First, A gives as much to B as B already has. And in the end, A gets what A now has. And how much does A have just before A minus B?
That means 20 kroner multiplied by 2.
And that's where we ended up. For A times.
Here
We're
are.
right in the middle of it. What about person B? First, B receives as much from A as B originally had. So they end up with 2B, right? But then we need to take something from B. We need to take as much as C has. So we just subtract C. And after that, that person ends up with. Notice that A, B, and C indicate how much money they had to begin with. Not later today.
That's where you need to keep your wits about you.
So person A starts with A kroner. Person B starts with B kroner. Person C starts with C kroner. Oh, so now we have the final equation. What about person C? Well, person C received just as much as they initially had. So now they have double. But in the end, we should also remember that C had to give as much to A as A now had. So we have to subtract this amount. Because how much did person A have after giving to B? That much.
And that's what we need to subtract from C here after having received it.
What C had originally. And that also needs to be at the end. And this is where the challenge lies in the task. It's about setting up the equations. It takes some practice. Now I will rewrite the equations in standard form, so we can plug it into a total matrix and perform Gauss-Jordan elimination.
That's what the method is
They have
called.
been practicing in class. It's called Gauss-Jordan elimination. And then we see about
It ends up getting the answers 55.
We should ideally do that.
Now the first equation, how does it look if I just rewrite it again?
The division is.
It says 2A, 2B skr in with 40.
So I write it as 2A, 2B, 0C. It should be equal to 40. Now it is written in standard form. Some number times the first unknown, plus some number times the second unknown, plus some number times the third unknown, should equal a known number. It's called a line of line. Then I do the same with the next equation. It says 0 of plus 2b minus 1c.
Should I give 40? That was your 2.
Written in standard form. Equation 3. Now we need to focus carefully. Minus a plus b. So it says
minus 1a plus 1b plus 2a. Honey, say goodbye. There are the three equations written in standard form. Then I write down my augmented matrix for the system of equations. And what was it again? Total matrix. It meant a rectangular number scheme where you put all the coefficients and the rest and stitch it together into a big matrix. So it should say 2. Minus 2, 0, 0, 2, minus 1, minus 1, 1, 2. The right side is 40, 40. And I'll just take a moment to check my notes to make sure I agree with myself before I start solving a system of equations that isn't correct. It is good enough.
I definitely got that earlier today as well when I was sitting and preparing.
Now we want to rewrite this total matrix into reduced row echelon form. And the method we use when we do that is called Gauss-Jordan elimination. So here we go. Chaos.
Hey, how's it going?
And if you want to impress someone with what you've learned on a study retreat, you should really tell them that Gauss-Jordan is this day's elimination. It sounds super tough.
And it's also intimate that they have made rainwater channels. Elimination.
So now I'm just looking through my notes a bit to make sure I haven't made any mistakes in the last few days. I would really like there to be a leading number 1 there. How could I get that? I could multiply row 1 by n. Then I write down this row 1 and multiply it by 1/2. If I multiply here by 1/2, then there is a 1 there, right? If I then add it up with that one, there's a 0 there. So I allowed myself to do that simultaneously. I said, I'll just take 1/2 times row 1 and add it to row 3. So I'm doing 2 things at once. Then I get that I am going up now. First, we need to multiply by 1/2 here, so it equals 1. Minus 1. And 0 becomes 0 times 1/2, which is still 0. And 40 times 1/2 is 20. So it should now say 20. Did you get that? In row 2, nothing has happened. Where can I see that? But there's nothing written out here. This is where you write what should happen in the rows. So nothing has happened. So I copy paste that here. 0, 2, minus 1, 40. But what did I do down here? Oh yes, I took half of that and added it to that. Half of 2 is 1. Plus 1 and adding -1, that's 0. Half of that, that's -1. Added to that. Half of that is still 0. Added to that, it's still 2. And half of that, it's 20.
Taken badly.
Yes, it's boring.
Is it okay? Do I agree with myself?
Then I look here and think, oh, I want a 1 in the diagonal. And I want zeros outside of the diagonal. 0, 0, 0, how nice. I already have zeros below the entire diagonal. But I want the diagonal to consist of only 1s. That's called leading 1s. So to get a pivot there, I just multiply directly by 3 with a pen. And have I done anything else? Oh yeah, I can also just multiply row 2 all the way through. With an R. What do I get then? Well, I haven't done anything here. Because then there would have been something, right? So I haven't done anything. So I just copy paste for myself. 1, minus 1, 0, and 20. And down here, it will say 0, 1, and minus 1/2. And 20. And down here, it will say 0, 1, and 30, because I'm multiplying by half, right? Just take a look at what it says now. 0a plus 0b plus 1c should equal 30. So what is c? 30. So Chantal apparently has 30. We knew that quite well. But only because we started with the solution.
So what's the idea?
Oh yes, then I can say half of row 3 added to row 2. If I take half of that one and add it to that one, what do I get out of it? Then that disappears and turns into a little 0.
So I am taking half of row 3.
And add it to the row. And in which row do I do that? In the row it corresponds to. So it's not ideal.
So now it's going to say this here.
1 minus 1 is 0 and 20. Because I haven't done anything there. And down here I should say that half times that is added to it. Half of 0 is 0. And on top of 0 is still 0. Half of 0 added to 1 is still 1. Half of 1 is 1/2. Added to negative 1/2 is 0. Half of 30 is 15 plus 20.
It's 35.
And down here, nothing has changed. Because if something had happened, there would be something written out here. So it says 031. So now we can see that 0a plus 1b plus 0c gives 35. So how much do you have? 35. Now we are almost done. The last thing I need is just to get a 0 there. And then I have 1s on the diagonal, leading ones. And I've got 0s outside the entire diagonal everywhere. If only I can get a 0 there. So I just take row 2 and add it to row 1. So I will write that up here. I am adding row 1 to row 2. And what does the sign say here?
I can never remember my license plate number.
We're done then. If I take this one and that one, that makes 1 in total. This one and that one make 0. This one and that one make 0. This one and that one make 55 in total.
And here we haven't done anything, so we'll copy paste from ourselves.
And now we are done. Here are the results. If you have not learned this method, you have to be quite creative to solve the system of equations, because you'll get these 3 equations here. Then you have to combine them in some clever way to extract A, B, and C. Can it be done? Yes. Is it difficult? Yes. And if there were 4 wires with 4 unknowns, is it still possible? Yes. Is it almost impossible to figure out how that possible solution should happen? Yes. But this method is systematic. And once you learn it, it just flows. And we were even incredibly lucky that no fractions showed up. Well, a few. But at least modest fractions. Can you see it? Cool tool. Why should we bother learning to do it by hand when you can just plug it into software? I mean, no regular person wants to sit and do it by hand if it's 5 equations with 5 unknowns. But since none of us here are ordinary, we're up for it. Now, we do not want to do that. We will do it digitally. But you need to understand the method. And later in the course, you should also understand geometrically what's happening as we do it. Because it turns out that what happens geometrically is quite magical, if you can visualize it. And there is a guy on YouTube who is unparalleled at making YouTube videos. He has a YouTube channel called 3 Blue 1 Brown. No, that's not Jim. 3 Blue 1 Brown. And he has made a series of videos on exactly this topic we have here called linear algebra. I think there are 15 videos. And once we have gone through our curriculum, I highly recommend watching his 15 videos because he has programmed in Python. So all the insight he gained while studying mathematics at university, he has essentially programmed into something visual. This allows us to see what's happening in his mind when he thinks about it. And it's really well done. It's like you get chills when you're into mathematics and watch those visualizations. It's like a total revelation. So I highly recommend checking out his channel. He also covers complex numbers, Fourier transformations, and all sorts of other advanced mathematics. So it's an insanely cool channel. Are there any questions about the example with Anders, Børge, and Chantal here? It's over here, but you need to practice to get it down. You need a bit of practice thinking through the equations.
And as you just found out yourselves, you need a bit of practice to do this.
So what is it that I'm actually doing when I do it? I start by thinking that I'd like a number 1 here.
And 0 this one, and 0 this one.
So I'm standing by it first. I make sure to get a 0 there and a 1 there. Then I use that to get a 1 there and a 0 there. And then I use that to get a 0 there and a 0 there. So that's the method. If there is a complete mess, you get rid of the complete mess.
So it becomes transformed into that number.
You multiply by the reciprocal of 2, which is 1/2. If there's a 9 there, then you multiply by the reciprocal of 9, which is 1/9. So if you're not quite sure what to do, it is a good place to start. If you need to change a number to a 1, multiply by the reciprocal of the number that is already there. Basically, 1 over the number. Benjamin. I start by making a 1 there. How do I do that? I multiply the entire row by 1/2. Then I want to get a 0 there. So when there's a 1 here, I take that one, add it to the -1 there, and then I get 0. But I do that throughout the whole row. So I do exactly what I wrote. I take half of row 1 and add it to row 3. What is half of 2? 1. Then add it to -1 and you get 0. So half of -2, because you were supposed to take half of row 1, and I am still in row 1. Then take half of -2, which is -1, add it to +1, and you get 0. Then take half of 0, which is still 0, add it to 2, and you still have 2. Take half of 40, which is 20, add it to 40, and you get 60. The strategy is to start by getting a 1 there and 0 below.
And I was so hyped up, it was already 1-0.
Well, the story started there, and then it's here, and then it's here, and so on. These are young people aged 15 to 18. And what's scary is that sometimes there's a freshman who practically solved the whole problem set. And those tasks are difficult. When I taught at Haraldsson Private Gymnasium, there was a guy who participated in the Give More competition and was a first year. He was one of those who scored the most points in Denmark. So sometimes there are people who like to sit and do mathematics for fun. And he was one of them. All right, if there are no questions, we'll continue. Let's now take a closer look at the concept of linear dependence and linear combinations. So here it is on board 4. Okay.
We will look at the concept of linear dependence.
And I already have to talk a little bit about it from last time. It was something about ingredients for making pancakes. Two vectors are said to be similar and dependent if one can be expressed as the other by multiplying with a constant. So if this is a vector A, what happens if I multiply this vector by a number? It will then lie on the same line as A did.
So now I am drawing a line
through the A vector. And what I am really saying is, no matter what number you multiply vector A by, you get a new vector that still lies on the same line that A spans. It's said that A spans a line.
And that means if I draw a vector that is placed here and call it B.
So, because B lies on the same line as A, I can be sure that the lines are dependent. Because I can take vector B and create it by taking an appropriate constant K and multiplying it by vector A.
Are you in on it?
If B can be written as a constant times A, then they say that the two vectors are linearly dependent.
So A vector and B vector.
He looked annoyed.
Depends.
And what that means in relation to our pancake story is that we're not really talking about two different ingredients at all.
It's the same ingredient, written into scales.
So if this is flour,
Here is just some more flour if the scale takes a little longer.
still the same ingredient. There's no new information in that vector compared to the other one, understood in the way that they span the same line.
So there is no more geometry information in it.
That means if you are a being living in one dimension on the line that vector A spans, you can never see anything outside of that dimension if you only have vectors A and B. You have no idea that other dimensions exist. No matter how you combine vectors A and B, you end up on that line. Think about it. Take twice this ingredient, plus 3 times this ingredient. What does that give? Well, 2 times vector A is twice as long. 3 times vector B. It is twice as long in that direction. Then add them together, and you end up on the line again. You always land on that line no matter how you combine RB. Can you see that? That means if you are a being living in a dimension on this line, you have no way of knowing that other dimensions exist as long as you only have vector A and B. You are simply forced by your destiny R to live on that line for the rest of your life. And you will never know there's anything else. But as soon as you encounter a vector that jumps off the line, a whole new world opens up in 2 dimensions. Now you can land anywhere in 2D using the 2 vectors. Okay, it's mind expanding to know a vector.
Breaking out of line, suddenly a whole new dimension unfolds.
But if I have yet another vector, which is not the same as those ones, but goes out of the board, then 3 dimensions open up to you. That's even more mind expanding. Now we have 3 linearly independent vectors. They span the space. So it takes exactly 3 linearly independent vectors, no more and no less, to describe 3-dimensional space. Okay, continue from there. Yes, question.
It's totally fine when I say something that's so nonsensical.
1 more dimension than 3?
I do not know, because I am forced to live in 3 dimensions just like you are.
If you want to have an idea, you might as well eat something psychedelic. Then you might get an idea about it. I don't know what the 4th dimension looks like, because I have not been there. And that's why I cannot draw it for you. But we can imagine it abstractly. You can imagine having 4 vectors in 4 dimensions with 4 coordinates for each vector. And none of the vectors can be written as a scalar multiplication of the others. So they are exactly independent. And that will span a mathematical 4-dimensional space, so I can only see it as an abstraction. I cannot imagine it in my head, because I have always lived in 3-dimensional space. But here's something you should hear, because another way to think about linear dependence is this. Can you take a number and multiply it by vector A, and a number and multiply it by vector B, so that when you add them together, you get the 0 vector? Let's just try to write this down. Is there a number S that I can multiply with vector A, and some number T that I can multiply with vector B, so that if I do that and add them together, I get the 0 vector? There's at least one solution that definitely works. Multiply vector A by 0, and it becomes the 0 vector. Do the same with vector B, and it also becomes the 0 vector. Add these 0 vectors together, and you get the 0 vector. Are there other solutions besides the one where there are 2 zeros? Yes. Look here. Take 1 and multiply it by the A vector. Is this one a little longer than that one? You can see it below. Is B a bit longer? Yes. So take 1 and multiply the A vector. Then take minus 0.8, because I just need to make it a bit shorter.
Hey,
I
am not doing that.
So I need
No
to
way.
switch.
I am not doing that.
I should not do it like this. Plus, so I need to say plus 0.8 times the second one, so it gets just as slow as that. Now let's try the B vector.
There, what do I get now?
Well, it's in sync. Can you see it? So it was a solution that worked where it was not 0 and 0. If there is a solution that works and is not all zeros, then the vectors are linearly dependent.
See you, yours.
Independent. So the only way to get the 0 vector is if you multiply all the vectors by 0 before you add them together. That's another way to see it. And you should sit down and think about it a bit more. Are there other solutions besides this one? Yes, infinitely many, of course. Imagine that I double the length of vector A.
then it becomes twice as long as Norway stretches us. And then you take this vector and multiply by 1.6. And when you add them together, you will also get, can you see it? So there are infinitely many ways to get the zero vector by combining A and B if they are linearly dependent. That is, if they lie on the same line.
Certainly.
Now imagine this situation. Here is vector A, and here is vector B. And you can now see that this is the case.
Two different ingredients. Because vector A spans this line and vector B spans this line.
And by combining, I can go anywhere I want in the plane. So they span it.
Two-dimensional space, the two vectors.
For example, can I form this vector C using A and B? And yes, I just multiply A by a suitable number, and I multiply B by a suitable number. If I multiply A by a suitable number, it becomes longer, or shorter, or changes direction. Are you with me? If I multiply B by an appropriate number, I change direction.
It is also lengthened?
Or the other way around. And where I want to end up is right there. So I take this line and shift it down here in parallel. And then I take this line here and shift it slightly upwards. Why? Well, that's how you add vectors together. So you can see that if I take vector A and multiply it by a number, it reaches out to there. So this is vector S times vector A, where S is an appropriate number. And then I take B and multiply it by a number, so it reaches out there. So this vector here is some appropriate number times vector B. Can you now see that this vector added to that vector gives that vector? It's the parallelogram rule. So in other words, I can form any vector C anywhere in the plane by linearly combining vectors A and B, as it is called. That means by scaling vector A, scaling vector B, and then adding them together, I can end up wherever I want. And the reason I can do that is because of the two different ingredients. So I am not forced to live my life in one dimension here, or in one dimension there.
Dimension here.
I can live my
Life
life with
over in
everything.
the plan.
And I have two paths independently in vectors. And if I now look at this equation, it is the smallest number I can multiply by AEV. And numbers I can multiply by
Times
AEV.
the side effects.
So it's dead
Critically
now.
important.
If you put yourselves in this context
First, I need
and
to
think
use
about
the
what
same
you are now,
against it.
since you are like this. Yes, there is an S and there is a T, but there is no T.
Just the ones and one
T that works, and they both have to be 0. Because look, if I multiply this vector by 0, it does this and becomes the 0 vector. And if I multiply this vector by 0, it also becomes the 0 vector. And the 0 vector plus the 0 vector equals the 0 vector. But that is the only solution that exists. Because the two do not lie on the same line, so I cannot get them to cancel each other out. It is impossible. They cannot cancel each other out unless I multiply them by 0 first. Then they cancel each other out in that way, where 0 factor plus 0 factor gives 0 factor. Do you see what I mean? So if this equation only has one solution, and that is S is the same number as T, then it's the same number as 0. I guess that's it. If S equals T equals 0 is the only solution, then that indicates independence. If that is the only solution to this equation, then it is the only solution.
And I could call it the guiding star, just to call it something to alignment star. Then A and B are linearly independent. A and B firm.
Right nearby. I'm hooked too. And what does that mean? It's just when you're hanging there, they stretch the plan. That lays out the whole plan.
This is the same as saying that A and B are together.
Spans the entire two-dimensional space.
And this thing about not having come up with the writing here.
They span the entire R2, so they say.
A real axis is a two-dimensional number space. It spans them. But only if they are similar are you independent of them. And what does that mean? They are not parallel. That's how most people like to think about it. If A and B are not parallel,
So they're each their own ingredient. It's salt and flour for pancake batter. And you can't get salt by taking an integer or a multiple of flour. They are each their own ingredient. So this vector contains new information relative to that one. But this vector does not contain any new information compared to that one. Why not? Well, it is just a written version of it. So it does not contain any new information. So every time we discover one more dimension in this universe, we've truly discovered a new vector that is independent of the one we knew before. That was a very esoteric explanation. We will get back to it later in the course, where I'll explain it more mathematically, but I like those stories. They're easier to remember. Because you can visualize it.
Let's try to solve it now.
A problem called a linear combination problem. You'll see what it turns into. It becomes a linear system of equations. Let's try to solve it on the next board. And after that, we might take a break. So you can look forward to a break in a little while. Here comes board 5.
Okay, so here's an example.
Here I have a vector called vector A. And what we're working on now, that's linear combinations. For those of you making a heading, and maybe I should make a heading myself.
In need A.
Combinations.
I'm just making a vector here that I'm fabricating called 1 over 3. And here comes another vector that I just made up, which is called 2 over negative 1. And here comes a third vector, which I just came up with, called 2 over negative 1.
Tap, 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 tap. It's called 5 plus 1.
And this question I am now asking myself, I will draw for you. So it's not just pure abstraction, but you can see it. The question goes like this. Can you know if there is a number s that I can multiply by vector A? And can you determine if there is a number t that I can multiply by vector B? So that when I take s times vector, A plus t times vector B, I get vector C. That's my question to myself. It needs to find such an s and such a t so that this is true. And what I have written here can be drawn because I know the vectors, so let me try to draw it. So here comes the drawing. Okay, I'll start by drawing the switches. It goes 1 out and 3 up. So let's say it looks like this. Said it was important to say. And vector B is called 2 over negative 1. So it goes 2 out and down 1. So it looks like this. That is vector B. And vector C goes 5 out and 1 up. So 2, 3, 4, 5 out and 1 up. So it's here. And what I am interested in is there a factor that I can multiply on this vector, which was off? And is there a number I can multiply with this vector, which was off? So that when I add them together afterward, I get C, which is this weight. And I hope you can see from my drawing that the answer is yes, because A and B are not parallel. And because they are not parallel, they appear to be independent. And because they appear to be independent, they span the entire two-dimensional space. And since the C vector exists in the two-dimensional space, is it possible to create it using the other two? Yes. And we can actually see from the drawing that it's possible. I just need to draw a parallelogram like this. It looks like what I need to do is take about 1 vector A and maybe about 2 vector B. And that balances things out. But let's see if it is correct when I calculate it. When I calculate this, 2 equations with 2 unknowns appear. A linear system of equations. So let's try s times vector A, that is s times this one. So I need to take s and multiply it with the vector 1 over 3.
Then I need to take t
And multiply by the vector.
B, but it was over -1.
Yeah. And it's
Hope
called
Monday is gone soon.
Called 5/1.
Let's see if I can find s and t, so the numbers add up. But I've learned that when you multiply a vector by a number, you have to multiply both the first and second components.
So what does it actually say here? It just says 1s over 3s, right?
And it should be added to the vector
2t over minus the. So I just multiply
both
t
first here
and
as
not
well.
the grain.
And over on the right side, the vector 5 over 1 is still there. But I have also learned something else. When you add two vectors, you add the first coordinate to the first coordinate and the second coordinate to the second coordinate. So here it says s plus 2t should equal 5.
It's one equation with two knowns, so I'll just write it down. N is plus 2t. It should give 5.
That was equation 1. And equation 2, 3s minus t should equal 1.
3 is minus t, that should give 1. And that's what you saw.
So what you can see I got out of it are two equations with two unknowns, namely s and t.
And there we can use chaos in order in elimination.
For what? To solve a geometry problem.
As it sounds, you can create the weight by using the 2.
Okay, one could see it as a bodybuilder problem. Let me explain what I mean. Imagine you need a force pointing in that direction, which is as strong in newtons as what this weight takes a long distance. And you have two people who need to try to do it together.
I have Paul and I have Benny.
We can see that Benny doesn't need to go to the gym because we only need one of him.
But Torvald has to train until he gets strong.
If we then combine Paul and Benny and add their strengths together, we get the desired force. So what we are figuring out is how much you need to bodybuild. Because S and T are the factors that tell you how many times you need to bodybuild.
How strong have you gotten, Jens?
You will be trained before you start.
I cannot really be more specific.
Let's try to solve it by setting up a complete matrix.
Stop.
And that means we focus on the
There's
coefficients 2, 3, 1, and then augment.
It's called 5D.
And then we proceed with Gauss-Jordan elimination until we found the bodybuilder coefficients S and T. We already have a number there, and we like that because we want that. But here we do not have a 0, so we will try to get one. How? We take row 2 and subtract 3 times row 1.
So row 2 minus 3 row 2. 1. And whatever we get, we will write as the new principal. So what does that give us? Let's keep calculating here. I haven't done anything up here, so it still says 1, 2, and 5. But here I say 3 minus 3 times 1, and that gives 0.
I say that minus 1 minus 3 times 2 is 6. So minus 1 minus 6 is minus 7.
Bandit, hold on. I can feel you a bit.
I did minus 1 minus 3 times 2.
That was minus 1 minus 6, which is minus 7. And here I say 1 minus 3 times 5. 3 times 5 is 15. And 1 minus 15 is minus 14. So here it should be minus 14. Now I would like a 1 there. Why? Well, because reduced row echelon form means 1s in the diagonal and 0s outside the diagonal. So if I need a 1 here, why not multiply the entire line by the reciprocal of negative 7? So divide the row throughout. You can think of it like that too. So I take row 2 and multiply it by negative 1/7. And negative 1/7 times negative 7, well, that must be 1.
So when I calculate further, it says 1, 2, and 5. And that one I haven't done anything with, so we can skip it.
There will be 0 times. Minus 1/7 is still 0. Minus 7 times minus 1/7 gives 1. And minus 14 times minus 1/7 gives 2. Is that okay? So now I have 0 there, 1 there, 1 there. So I just need that 0 there.
I'll just take row 1 minus 2 times row 2.
Row 1 minus 2, row 2 of, and figure it out. So minus 2 times 0, that's still 1. 2 minus 2 times 1, that's 0.
5 minus 2 times 2.
They okay? And down here I have not
It
done
still
anything.
says 0, 1, and 2.
Sweet. Because our guess was actually right. How lucky can you get? And on a Wednesday, because what it says up there is that 1 times s plus 0 times t must equal 1. But that must mean that s is 1. And here it says that 0s plus 1t equals 2, so t must be 2. It says it must be 2, and we can see that it fits perfectly. But this person does not need to train at all. He's as strong as he needs to be, so he doesn't need to go to the gym. But this one needs to train until he is twice as strong so he can deliver the force, where now 2b plus 1a will equal c. And they say that vector c is described by a similar combination of vector a and b. You have simply combined them linearly. And what does that mean? You have multiplied by constants and added them together. And that is the only thing you're allowed to do in a linear combination. And that is the only thing that happens in linear systems, multiplying by constants and adding together. Constants are being multiplied. Here it is, the -1 constant that is multiplied and added together. Can you see that? Good job, Towers.
So if anyone wants to pause the recording, we'll take those 10 minutes.
This is the final round before we finish here in about an hour at 3:40 p.m. We're going to dive a bit deeper into some examples so you can see what it means geometrically, this thing with linear equations and linear equation systems. Maybe you remember from last time the straight line. The straight line can be described in several different ways. You could write it like this: y equals x plus b, where it is the slope coefficient, and it is the point where it intersects the y-axis. And then you could also describe a straight line like this: some number alpha times x minus x sub 0 plus some number beta times y minus y sub 0 equal to 0. Maybe you have already forgotten it, but this is also a straight line.
And which straight line is this here? That is the right line.
It's a completely unique guideline. So that's the guideline we should have, which has the normal vector and with coordinates alpha over beta. There's the one that switches normally, and which passes through the point with coordinates x0, v0. Oh, sound. Contains the point. When we say that a straight line contains a point, it simply means that the point lies somewhere on the line. P0 with the coordinates x0 or u0. So if we draw it, so we can start by thinking that there are
straight lines, but I will get through it.
Point here. If this is point P here.
But there is only one straight line that goes through this point and has to be perpendicular to this vector. And the only straight line that goes through this point, which is perpendicular to that vector, is the one I'm drawing now.
Imagine it being 90 degrees.
So that's another way you could describe a straight line, like that.
So there was also a way to describe a straight line like this. Now I would like to describe the loan. And now I describe the loan like this: x over y, it's just right.
X0 over Y0.
Plus the number t, which we call a parameter, multiplied by a direction vector with coordinates r1 over r2. And it can take on any real number. And there was also a drawing that went with that story. So if I have a coordinate system here with an X and a Y axis, and if this here is the line, then this is the line. So we just say that you can describe the line by knowing a point that's on the line, P0, and by knowing a direction vector. Is a vector for the line, that is a vector that is parallel to the line. From that point, I can reach all points along the line by first moving from the origin to that point, where it's a vector called x0 over y0. And I can scale this direction vector so it becomes longer or shorter or changes direction by letting t be either positive or negative in some value. And in that way, I can land anywhere on the line. So the straight line can also be written in this form.
And that is what we call the standard parametric form.
Let's now use everything I've just explained to take a fresh look at the line. So here's an example, and I'm taking it from my notes. So here, for
That's
example,
it. Let's see, I have a line that looks like this.
2 times x1 plus 3 times x2 equals 8.
What is that? That's a weird line.
What is it again? It's one equation with two unknowns. I don't know either x1 or x2. Can I solve it? Yes, I can. But is there more than one solution? Yes, there is. Because it's a line. So all the points that lie on the line solve the equation. So how can I draw this? Well, I can recognize this as a straight line in an x1, x2 coordinate system. Now it's not called xy, now it's called x1 and x2, because they are new names I've come up with. So I can actually draw that straight line. So let's just try this. Here is exit the event, and here is grown up x2. It's just a regular coordinate system. Now it's just not called xy, it's called x1 and x2. And do you remember when something looked like this? It had a normal vector with the coordinates 2 over 3. So you can read that off. The normal vector is called already over 30.
Do I reach a point, that direction before I go through? No.
I cannot quite see it right away, but I can figure it out. I can just say, what if x2 was 0? If x2 is 0, what would x1 be then? Well, if x2 is 0, then this part is 0, because 3 times 0 is 0. When it says 2 times something you do not know must equal 8, and what you do not know must be 4. So x1 equals 4. I have a point now. My point is called 4. Start from 0. That's my point. Point 0. Are you with me on that? So that means I know that this line passes through the point 4, 0. Let's say it's here. 4 and 0 up. So my line has to go through there. And there are infinitely many lines that go through there. But there is only one of them that is angled correctly from the normal length. So now let's draw that direction vector. It goes 2 out. This is 2. Then it goes up 3. Maybe there. So this is my normal vector for that line. And now there is one and only one straight line going through that point, perpendicular to the vector. And it's roughly here. Something like that. Here are 90 degrees. So this line, that's my straight line. So this is a linear equation. And how many solutions does it have? Well, it has all the points that lie on the line as solutions. Let's try taking one of the solutions. There, that was a solution because it's on the line. Try setting x to 4, x1 to 4, and x2 to 0. Does that solve the equation? 2 times 4 is 8, plus 3 times 0 is 0. 0 added to 8. Is it 8? Yes, it is 8. That solves the equation. But you'll notice, no matter which point you choose on the line, the combination of x1 and x2 will solve the equation. So how many solutions does this equation have? Infinitely many. Specifically, all the points that lie on lone, where x1 and x2 variables are valid and correspond to each other.
And when you put them in, the equation is true.
You see what I mean? So this is one equation with 2 variables, and there are infinitely many solutions. Geometrically, it is all the points from the line that are solutions. I hope you can follow me on this. So for example, this point is a solution. This point is a solution. All points on L. They combine x1 and x2 in a very specific way that exactly satisfies the equation. So how do you express the solution to this equation in standard parametric form? Here it comes. What does this solution look like in standard parametric form? You do the following. You just look at this equation here, called 2 times 1.
2 equals 1 plus 3 is 2.
Line with 8.
And then you say, okay, I cannot find x1 unless I know x2. So I let x2 be a variable I can change. This is called turning x2 into a free parameter. So I am saying now, let's imagine that we set x2 to be called t. Because then we know that at is something that varies, and that's what you call a parameter. Can I find the exit now? Yes, I can. Let's try to isolate the exit. If I need to isolate the exit, it should go over to the other side of the equal sign, and then I should divide it by 2. Can you see that?
So that must give -3 times 2.
-3 x2, but x2 was t, and then I have to divide by 2 at the end, because I need x1 to stand alone. And the 8 also needs to be divided by 2, so there's going to be a plus. Let me explain that again. I'll isolate x1 by subtracting 3x2 from this side. So it says 8 minus 3x2, but I had called x2 t, so it says 8 minus 3t, and that needs to be divided by 2. So the 8 becomes 4 because it is divided by 2. And minus 3t becomes minus 1.5t because it is divided by 2. So now I know that x2 is t and x1 is something that depends on t. And now I can write the solution to this equation in standard parameter form. And it looks like this. That is the standard parameter form. So I need to copy this notation and insert the correct number. Then I'll have the solution. So it looks like this. x1 and x2. What is a phenomenon, Tim?
Yeah, there's some kind of point, you see.
Plus t times some vector. And then I just need to fill in what should be here. So let's try to fill it out. What is x1 equal to? x1 is equal to 4 minus 3 halves t. So I'll just write 4 here. And then I'll just write minus 3 halves here. Now it fits, because what does x1 become? It becomes 4 plus t times minus 3 halves. That's exactly what it should give. And what is x2 equal to? T? Well, then it should just say 1 there and 0 there. Try to see, what is x2 equal to? 0 plus 1t. So what is this?
That is the solution to that similar alignment.
And what is that? A straight line. And in what direction is that? It is the direction that passes through the point with coordinates 4, 0, and has a direction vector with coordinates -3, 5 over 1. And if you draw it, it will lie right on top of this one, of course. Just described in a new way, described in standard parametric form. It is said that here there is a single infinity of solutions. Namely, a solution for each chosen value of the parameter form. Why is there an infinity of solutions? Because there were more unknowns than there were equations. There was only one equation, but there were 2 unknowns. And because there's only one equation but 2 unknowns, you get a single infinity of solutions. Now you will see an example where I have one equation with 3 unknowns. This results in a double infinity of solutions. And there, the solutions are not a line. They form a plane in 3-dimensional space. Are you ready for it? So let's move on to the next example. What I want to show you with this example is, what is a line and an equation geometrically? That, for example, is a line. But it could also be a plan. But it could also be a room. And the room can be 1,000-dimensional if it needs to be.
Okay, so
if I can wipe the board, I'll continue with the next story. So board 7. And you might have to go home and watch this video again, just to make sure it made sense. Because you need to get used to this way of thinking. But once you get used to it, It's actually not that hard. But I remember when I saw it for the first time, I thought, what is this about a simple infinity of solutions? It had become part of that it's all geometry. That everything can be drawn until we move over to 4 dimensions. Then unfortunately it cannot.
I have a couple more examples if you want.
We will show you. So I'll just take the example from my notes to make sure it doesn't get out of hand. Example 2.
I have here a line called 2 times 1
plus 3 times 2 x3. Babe in 5. So you look at it and say, how many unknowns are there? 1, 2, 3 unknowns. How many equations are there? What does the solution look like in standard parametric form? It becomes an infinite set of solutions corresponding to a plane in space. And all points that lie on this plane have a combination of x1, x2, and x3 that fits exactly what the equation specifies. Okay. By the way, if you remember what I had the other day, which was the equation for a plane, you'll see that it is the equation for a plane. Which plane is it the equation for? It is the equation for the plane that has the normal vector with the coordinates 2 over 3 over minus 1. Can you read off a point that you know the plane goes through? No. But can you quickly find a point that the plane goes through? Yes. You can just set this to 0 and this to 0 and find x1 as 5.5. Then you know it passes through the point with coordinates 5.5, 0, 0. The plane goes through this point, for example. But note that it is all the points in the plan that solve the equation. So here's the equation for a plane. And what that means is, if you pick a point in space and it happens to lie on that plane, then you know that plugging in the combination of x1, x2, x3 here will make it work. That's what it means.
But now we need to introduce 2 free parameters.
So can I find x1? Yes, but only if I know x2 and x3, so I can't. So I say, okay, let's call it x2. Let's call x2s, and let's call x3t.
because then you indicate the names.
That there are some free things that can just be allowed to vary. We call those free parameters, these 2. They can vary, so they are variable.
Let's try Phoenix 1.
What will be the exit? Well, if I need to isolate exit, then I have to move it over to the other side. And I have to get this term over to the other side. And finally, I must remember to divide. So let's do it step by step. I'll wait to divide by 2. So it will say 5.
Minus 3 times x squared.
Plus x3. Can you see it? I just moved that term to the other side, so it becomes a plus. And I've moved that term to the other side, so it becomes a minus. I just divide by 2 to find x1. That is 5 halves.
Minus 36.
It is 3 halves plus 2 and plus 1 half. See you next time. But egg 2 was exactly what I had decided to call egg. And egg 3 was exactly what I had thought of calling egg.
Yes.
So I put it there and there.
So now I'm finding the exit expressed.
With the 2 free parameters s and t. So it will say 5.5 minus 3.5 times x2. But that was s. And then plus half of x3, but x3 was t.
So now I can write down the solution in standard parametric form. Here's the solution. Here's what the solution looks like.
What exactly am I supposed to solve? I need to find x1, x2, and x3. There are 3 unknowns. There is only one equation. And since there is only one equation with 3 unknowns, you get a double infinity of solutions that look like this.
x1, x2, x3.
Like some fixed point.
Pusher, the time England is far away then.
And plus
t times another vector.
Now the structure looks like this because there are two free parameters, so I just need to fill it out.
What is x1 equal to?
5 halves. Does 5 halves have anything to do with S and T?
No, it should stand here alone.
Yes, I need to have 5.
And why should it be Dusty? Well, that's because I'm looking for x1.
And not his vacuum cleaner.
X1, does it have something to do with S? That's why it should say 3.5.
It's actually so easy that it's almost hard.
You just need to pause and think.
And what got it going?
Does X1 have anything to do with T? I have half of T, but then it should say half here, right? Does it fit now? What is X1? It is 5 halves plus S times minus 3 halves plus T times 1 half, and that is exactly what it says.
What is x2 equal to? It is easy.
X2 is just S, so there should be a 1. Is there something you can do? Is there any constant involved? X2 does not have a
Something
gender.
like that, or maybe something about T-pods.
Art and
In
real.
any case, there need to be numbers over there, S.
What is x3 equal to? Is it equal to t?
I can just see that I'm applying trees on
With
the way.
T, there should be a 1 there, but it has nothing to do with S, and there is no constant on it. It says licensing.
And what is this? It's a plan.
Where in the room?
Which space is 3-dimensional? And there are 3 channels.
So look here, what it is. It is a vector in space. Are the two equally independent of each other? Yes. You cannot handle them one at a time with a constant and then get it.
You can't do that because you can't have a beer and
So we have a constant, and then you get one.
So the two vectors are linearly dependent, which means that they span a plane since they are linearly dependent.
And this shows how far the plane has moved away from Aarhus.
So if it says that first you should move as far away from the origin, then you build your plane. So we do it like this, away from the origin, and then we build a plane. And all the points that lie in that plane satisfy this equation. Therefore, all the points are the solution set for the equation. So this is the standard parametric form of a plane, where both S and T can vary freely in the real numbers.
We'll just write that down. This is a plan.
Living in R3,
That's the mathematician's way of saying it exists in 3-dimensional vector space.
why do we say it has a double infinity of solutions? It is because there are two free parameters. So to get an equation with 3 unknowns has a double infinity of solutions, and all these solutions correspond geometrically to all the points on a plane in the 3D material.
Any questions?
It's just an
If
illusion.
it's gotten a bit abstract, it's because it is.
Let's go back to example 1 because we're not done discovering everything about it yet.
So let's just go back to example 1 for a moment.
How did example 1 go again? I've forgotten, so I need to check it here. 2x1 at 3x2. Put it in words. So now we can just pretend we've turned back time. What is this? It's a straight line. That's the first thing we think. Because we have learned that when something looks like this mathematical structure is the straight line. And which straight line is it? It is the straight line.
There's a normal weight country with canals
2 and 3.
that goes through a tower I can just find if I feel like it.
Thank you for today.
Are you following?
Also, it is a similar alignment.
It is a
Car with an aligning traffic.
influence of who? Exiles x2.
How many unknowns are there?
How many equations do I have? 1, because there is only one equal sign. In this situation, there is
eternity.
only one solution.
And everything.
Solutions, what do they correspond to? Points on a line that exist in 2-dimensional space.
Are you following so far?
And what was the solution like? I just wrote it down. I won't show it again. I'll just write it down now because we just did that before. the solution looked like this. And now I'm writing
There's
it down.
something really awesome about looking at this solution.
They're done. A few minutes ago, we showed that this is the solution given in standard parameter form for that division.
And what was this here? A guideline? Which straight line is that? It's the straight line that goes through that point of
It is
coordinates.
4 past midnight, and that uses this as a directional weight. Are you still with me? It looks like my solution has 2 parts. There's a part here, and then there's a part here. Let's see if we can understand what it is. If I set x1 to 5,
x4 and x2 to 0, does that work?
Let's first test VCX in the
4.
framework.
Then it says 2 times 4. So that's 8.
Plus 3 times 0, because x2 is 0.
0 plus 8.
is it true that it is done? Yes. So what is this? It's one solution. It's a very specific solution. In English, it's called one particular solution. Or in Danish, we say including a particular solution.
So this is a single one.
Articular
I have some.
pulea.
Oh, that is exciting.
One thing you should also know, by the way, is that if I had written 0 over there, it would be called a homogeneous equation, because that's what it's supposed to be called, since someone decided it should be called homogeneous if there's a 0 over there. So then you cannot just take 8 and subtract over here, so it says the 8, and then write 0 and call it homogeneous. That doesn't work. If there is a constant times x1 plus a constant times x2, and it equals 0, then it's homogeneous.
So it will not be even when pulled across on both sides of the stairs.
But then what is this? It is a single particular solution to an equation where there is not a 0. It is called the inhomogeneous, meaning the full equation. So this is a single particular solution to a homogeneous one.
The inhomogeneous equation.
Yes, it is that too. What we discover here is that this is the complete solution to the homogeneous equation if there was a 0. So if I try to look at the line given by the equation 2 times x1 plus 3 times x2 equals 0, which I'll do for you now, you'll notice that the solution to it is this,
Just without that one.
So now I'll just write down what this is. It's the complete solution for the homogeneous version of the line, where it equals 0. So this is it. Complete solution. Overall, complete means all solutions are here. There are no others. This is the complete solution. Solution
To the homogeneous version.
Is that a shooting star?
So I could just call this an encouraging star.
So the homogeneous version of the alignment is one where there's just a 0 over here. And I'm claiming that this is the complete solution to the alignment. And why am I making a big deal out of discovering this? It's because it's always true. It applies from 10 equations with 10 variables.
Right now, I like it.
And it applies from 2 equations with 2 variables.
The same applies to an equation with 2 unknowns.
For linear systems of equations, the solution always consists of a single particular solution to the non-homogeneous equation.
Plus the complete solution.
Put a homogeneous
It is a
one where
version
the
of the
0 is
equation.
over there. It always works.
And that's pretty wild,
Cool.
because
Structure.
it teaches us something about the structure of the solutions to your equations. That's why it's also called the structure theorem. That is the structure the solution has. And we are not quite finished discovering it, as I have only claimed it. So let me just show you that if there is a 0 there, then this will be the solution.
Okay, I will just do that over here.
So this is still example 1. I'm continuing over here now.
And I can figure that I will be tired.
I am looking forward to it, as there's not long left until we're done.
Here's an example.
I'm looking at this 2 by 1 plus 3x2 equals 0. So the homogeneous version of that equation, let's try to solve it then. Can I find x1? No, only if I know x2. So I introduce x2 as a free parameter that can be adjusted.
And then I can always find the exit if I ask if I have been
Choose a
outplaying.
specific x, meaning a specific t.
Same idea as before.
So what does x1 become then? x1 becomes 3x2. Can you see it? It just looks like that on the other side, you know, but divided by 2. So minus 3/2 x2. Were you with me on that?
I just take that term, subtract on the brackets, and divide by 2.
But x2 ferret can be referred to as t. So here it's minus 3/2. Then I can write down the solution. Here comes the solution in standard parametric form.
To that line.
The solution in standard parametric form is x1 over x2 equals. Now let's see, x2, it's just t. Then it should just say t times a 1 there. And x1, what is it equal to? It's minus 3.5 t, so it should just say minus 3.5 here. Just ask it like that, so it's not too cramped, like that. This is the solution, and t can be anything. So here are all the solutions, namely one solution for each selected value of. But what is this? That's exactly what was here. And that's what I claimed was the complete solution to the homogeneous
That's
problem.
true too, because if I look at it homogeneous, then I get it.
So I hope that example shows you that there is a particular structure in solving similar equations. The structure is that the solution always includes a single particular solution, even the inhomogeneous equation, that is the original equation, plus the complete solution to the homogeneous version of. And the structural theorem, it is so important because it also applies to differential lines. And we have reached that point. Linear differential lines follow the same solution structure.
And mathematicians love structure.
As soon as they can say something about some structure, they do it, whether you like it or not, whether it sounds difficult or not. Have you thought about this? Are the structures the same when you solve differential equations? No, I actually hadn't thought about that.
That's important. Make sure you remember that.
Because understanding something is about being able to put it into context.
In category and structure, we understand connections. And that's what we practice in mathematics.
Okay.
Yeah.
I'll just wrap up today by telling you about Wien alignment systems in general, and quotient matrices and total matrices. Okay, but now let's get into symbols, as I would if I were taking the monthly exam.
Let's take board 8, and that will probably be the last one for today. You all look totally exhausted.
Oh, okay, that's why. Okay, I will be cool and stick around a bit longer, right? Okay, so if you're at an oral exam and you're asked to characterize a similar and a similar system, what does that mean?
What is a linear
Equation system. You can explain something like this. Imagine I want to find the variable x1. It is something I would like to find, but what I know is that if you multiply it by a number a, this is just a number called a 1, 1, because it is a number that belongs to the first row I am writing and the first column I am writing. And then there is another number I want to find. which is x2, but it is multiplied by another constant that I call a 1, 2.
Why do I call
Have
it
1
that?
to 2. Oh, right. It's because it's
In
a
the
number.
first line, it says I'm writing.
We move to another column,
There's one more number I'd like to find, x3.
and it's multiplied by a new coefficient of
1, 2, 3.
and then this continues with increased complexity until he's ready to
The
sell.
last variable I want to find.
And now I just need to think about it for a moment. I'll call it xn, or he should have called it
That's the end. So
an
there's
earful. And because it's called the final unknown, it's also multiplied by some number that belongs to the first row, but it's the nth one. And all of this I know, that if you add it together, it equals some number. And since it is the first number, I call it B1. What is this? It is an equation. Too many unknowns. 1, 2, 3, 4, out to an unspecified number of unknowns.
Are you ready?
Then I say you have one more equation.
But now I'm in the second row, so it's not A11 anymore. Now it's A21.
I am now in the second row, first column, and that is also multiplied by the first unknown exit. Then I have a new coefficient, second row, second column, and it continues like this. Second row, third column, plus, break, plus. Second row, last column, multiplied by the last unknown should equal B2. And so the story continues down here because I have many equations. And of course, I cannot write them all down if there were 10,000. So I will just skip to the last one. And let's say the last one is number M. So now I'm in the MTH row, first column, and it is multiplied by the first unknown.
and then it continues AM2.
X2 plus AM3, X3, and then we continue this way until I reach the MTH row, last column, column times the mth unknown. And how many rows were there here? M, so this should be B1, B2, B3, down to B. So how many equations are there? There are M equations, which means there are M equal signs. So there must be M equations. And how many unknowns are there?
So there are M equations with n unknowns.
So this is ligninger.
Med
N unknown.
And if you knew how many students struggle to get it written up, if they postpone it to the final exam,
It's all jumbled up about what goes on all those spots there. And that's just because you haven't tried it. So I really recommend that you try it, explain it to each other, and write it down without having an order. You should just be able to stand and think that it has to be like this when you think about it, right? All of this, these are known numbers. Those are not the ones you need to find. Just like when I can see a board over there, it says 2 and 3 and 7 and so on. Those are all the coefficients. So these are called the coefficients of the system of equations. This over here is called the right-hand side, oddly enough. It's on the right side of the equality sign. So if you take a matrix, a rectangular array of numbers, and put all the coefficients in there, then you have a coefficient matrix for your systems. And it looks like this. 2 lines underneath to indicate it is a matrix. Capital letter, because matrices are written with capital letters in Denmark. Some Americans write a matrix with just a capital letter without the 2 lines underneath. You need to pay attention to that if you're Danish, because you really want those 2 lines to be completely sure it's a matrix. Especially when there are no rectangular number schemes. When you're just doing pure algebra with matrices, it's nice to have 2 lines under all matrices.
So it looks like this. And then we have to insert the quotients of 1.1.
1, 1 of 1, 2 out of 1, n, as in Norway.
And down here, A2, 1, A2, 2, out to A2M. and then down that way, down to AM1, because now I'm in the MTH row. First column, see first column, MT row, and then AM2 out to AMN. The reason why I paused earlier was that I wanted it to come in alphabetical order by AMN.
LMN, isn't that how you say it in the alphabet?
Hope you have a great evening. I can never remember that
Will
you start
improve
with
with
A.
less.
It is really annoying.
That is one of my weaknesses. So this is what we call a coefficient matrix for the system of equations. And all the unknowns, x1, x2, x3, those are the ones we want to find. We can put them into a column vector. So they put the column vector that describes all the unknowns, we just call the x vector. And note, there can be conditions in many dimensions here, so I underline it. One line, not two. If we just put one underneath, we know it's a column, and it's called x1, x2, x3, and so on, all the way to xn. So here they come. N as in needle. So that is a column vector. And then there's the right side, B1, B2, and it goes all the way up to B. M can be larger or smaller than N. It depends on the tasks. So the right side looks like this. B vector, just one line for that vector. And there is only something in one column. Technically, that is also a matrix, which has M rows and only one column. But a matrix with only one column usually has only one line underneath. Matrix just means rectangular number arrays. And that's what this is too. Because where are all the known right sides here? B1, B2, B3, B4, all the way up to BM. So it is B1, B2, and all the way up to BM, like in Mons.
And if you just stitch total, or if you just stitch creation,
along with the right side, you get the total matrix, which looks like this.
And then number matrix.
I know. And two stretches under that matrix.
You stitch it together by taking the coefficient matrix and merging it with the right-hand side.
And the right side was B. Here you get a matrix that looks like this.
Hey, 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 ding, ding. Out to A1, and what did I have then? N as in Norway.
And here it will say A2, 1A2,
A2N, A2N, down to A11, A12, until I need to make some dots out to A1.
And then you draw this dotted line, and out here you write B1, B2, and completely reduced BM. The x's are not needed at all. When we solve a linear system of equations, we do not deal with the x's at all. Now we only have all the numbers. So we have all the coefficients for the system of equations, and we have all the right sides. And that's it. And what is this little rascal here? It's a matrix. What kind of matrix is it?
Row and column peg.
We can just count how many rows it has.
1, 2, 3, 4, 5 out to M.
You need to say
First
the
things
rows
first.
you can decide on. So I think
it's an M, because I need to get the row number first.
multiplication. And how many silver?
Then it's
None.
2, 3, 4 up to N, and then one more. So it's N plus 1.
So it's an M. Multiply N plus 1. Matrix. That's good.
You just need to practice writing it down clearly. So it's not muddled in what you're actually writing. But this is the mathematician's way.
Write generally. What is DNA?
My system.
It's kind of like this. It's going to be a drainage system.
where there are n unknowns and m constants right in the middle of. And here is the complete matrix related to the general linear equation system. And you should ideally be able to tell that story in a relatively short time, if you are lucky enough to draw this question for the exam month. And that's why you need to practice it. Your hand has to know how to write it without hesitation. If you start thinking, then it goes wrong. When you're at an oral exam, your hand should know it, just like learning to play guitar. Tim Christensen can't be looking down when he's doing the Silver Flame solo. It has to just come naturally. If he starts thinking about it, that's when it goes wrong. Haven't you heard what musicians say? If they start thinking about a solo, knowing they have to play it, that's when it goes wrong. You definitely shouldn't think about it beforehand. Just play it when you hear the cue from the drummer, then it's on.
What?
It was definitely early for you to be let off today, but there you go. I'll recap some of it next time. But if you're unsure about what happened today, watch the video again when it's posted. Thanks for today.